In a single replacement reaction, a lone element will take the place of an ion in an aqueous compound. Aqueous ionic compounds have a positive half, called a cation, and a negative half, called an anion. Which half of the ionic compound the element will replace depends on what type of ion that element will form. In the case of zinc, in our first example here, zinc forms a positive ion when it's in an ionic compound. So it will replace the positive half of the aqueous compound, which is the hydrogen. When the zinc kicks out the hydrogen, hydrogen becomes an element. And remember, hydrogen as an element is diatomic, hence H2. This is the pattern of a single replacement. One element reacts with an aqueous compound to produce a new aqueous compound and a new element. In our second example, iron, being a metal, forms a positive ion, so it too replaces the positive half of the aqueous compound, which in this case is copper. When the iron kicks out the copper, iron then forms the aqueous compound with the sulfate ion, and then copper is the lone element. In the last example, the lone element is chlorine, which is a nonmetal and not a metal like zinc and iron. So chlorine, when it's an aqueous ion, will be a negative ion. So instead of replacing the positive half of the aqueous compound, it replaces the negative half of the aqueous compound, which are the bromides. Once chlorine replaces the bromide, chlorine is now in the aqueous compound with the iron, and then bromium is the lone element. One of the things you must do with a single replacement reaction is check to see if the reaction will even happen in the first place. To determine if a single replacement reaction will happen, you have to check the reactivity of the lone element and compare it to the ion it will be replacing in the aqueous compound. To do this, we use the activity series. In our first reaction, zinc is the lone element and it will be replacing hydrogen in the aqueous compound. So we start by identifying where on the activity series zinc is, and then draw a line to hydrogen. If the lone element is more active than the ion, then the reaction will happen. You'll see this as drawing an arrow down. I like to think of it as boulders will roll down a hill spontaneously. So if you're going down to the ion from the element, the reaction will happen. In our second reaction, silver is the lone element and copper is the ion in the aqueous compound it may replace. If we identify silver and copper on the activity series, we see that silver is below copper, so the arrow goes up. That's like a boulder rolling up a hill on its own. That will never happen. This is not a reaction. In our third reaction, iron is the lone element and magnesium is the ion in the aqueous compound it may replace. Again, when we identify the two on the activity series, because iron is below magnesium, that would be like a boulder rolling up the hill again. That reaction does not happen. In our fourth and final reaction, we have iron as the lone element and copper as the metal ion in the aqueous compound it may replace. Iron is above copper on the activity series. So here our arrow goes down. That's like a boulder rolling down the hill, which can happen on its own. This is a reaction. Take a moment to practice these reactions. If any is not a reaction, just write NR. But for the ones that are a reaction, predict the correct products and balance the chemical equation. Pause the video now and I'll show you the answers in a moment. So in this first reaction, zinc is above chromium on the activity series, so this reaction will occur. So that means in the replacement, zinc will combine with chloride. Since zinc has a +2 charge as an ion, and each individual chloride has a -1 charge as an ion, the correct formula for the product of zinc chloride will be ZnCl2. And then chromium is the lone element now as a solid. The biggest mistake a new student will make is to bring over the subscript that an ion had as a reactant to the product compound. In this case, even though you had 3 chlorides in the chromium chloride compound that you started with, zinc chloride is always ZnCl2 because zinc has a +2 charge and Cl has a 1- charge. Do not bring over the 3 subscript just because that's what chloride has as a reactant. Form a neutral ionic compound and then lock in these formulas and you can adjust the amount of matter you have using coefficients. We balance the matter on both sides of the equation using these coefficients in front of the compounds that tell us how much of each substance is needed for the reaction to occur. In reaction 2, looking at silver and aluminum on the activity series, hopefully you can tell that this reaction will not occur. It's no reaction. This is the same thing for reaction number 3 when you look at zinc and magnesium on the activity series. However, the fourth reaction does occur because magnesium is above aluminum on the activity series. So we have to predict the correct ionic compound of magnesium sulfate, which since they both have a +2 and -2 charge, it's 1 magnesium for every 1 sulfate. And then aluminum becomes our lone element. Now that we have the compounds, we have to balance the matter using coefficients. And then we're done. In chemistry, sometimes we don't want to look at the full molecular equation and we just want to see the change that's happening in a reaction. This is called the net ionic equation. The net ionic equation only shows what is changing. So it only shows a substance that either changes its state or its charge or both its state and its charge. Anything that does not change in a chemical reaction, we call those things spectator ions. They begin as aqueous ions and they end as aqueous ions. Their state and their charge does not change, so they are not included in the net ionic equation. To go from the molecular equation down to the net ionic equation, often first you have to write the full ionic equation. What the full ionic equation does is it translates the molecular equation into a truer version of it called the full ionic equation. The full ionic equation is a truer representation because if you have an aqueous compound, those two ions are not actually together. The molecular equation kind of lies and says that the silver ions and the nitrate ions are together as one compound, when in actuality, they are free-floating ions in the water, completely separate from each other. If you look at this particle diagram before the reaction, you can see that in the solution, we have silver ions floating around and separate nitrate ions floating around, and some solid copper down at the bottom of the beaker. And after the reaction, we see now we have solid silver sitting at the bottom of the beaker, and floating in the solution are the copper ions and still the nitrate ions, which is why we say that it's aqueous copper 2 nitrate. When we look at what's actually changing from the beginning until the end, the silver starts off as aqueous ions and the copper starts off as a solid. And then after the reaction, we see that we have solid silver and then aqueous copper ions. The nitrates start as aqueous ions and end as aqueous ions, so they actually don't change in the reaction and so aren't even part of the reaction itself. That's why we say that they are spectator ions, meaning they just watch the reaction occur. So when we write the net ionic equation, we do not include the spectator ions since they're actually not involved in the reaction at all. This reaction is actually the reaction between solid copper and aqueous silver ions. And that is what this net ionic equation shows us, which is a much more true representation of the reaction.